Okay, hello and welcome to this special session of OCA for a private screening of the documentary Luminous. Here on the panel, we have Sam Smart, who's the director of the documentary with us, and he's going to tell us all about himself and the documentary. And we have also John Hoot, an OCA board member with us. So let me remind everybody that you could use the raise hand function on the Zoom to send us any messages or answering the questions that you might be asked about being successfully registering, and use the chat if you have anything you want to send us. When we have the Q&A session, you could use the Q&A button on your devices to send us any questions you might have. So without any further ado, let me turn it over to Sam to tell us all about it. Sam.
Hi, everybody. Thank you so much for having me. I'm really excited to be here and to share this film with you, which is something I've been working on for a number of years and I'm quite proud of. This is a special pre-release screening, so the film is not out there in the world yet, but it will be hopefully next year. And so we're taking it around to astronomy clubs and saying, hey, would you like to see what we've been working on? I am a professor of communication at Calvin University in Grand Rapids, Michigan. And the main subject of my film is a professor of astronomy at Calvin University. So he's my across the campus colleague. And that's sort of how we got started on this story. The chair of the department, who you'll see also in the film, came and pitched this idea to me when the research was at its very, very earliest stages. So that was our sort of special access to this story. And it's also what we would call a longitudinal film. So instead of a sort of science topic, you know, the Event Horizon Telescope or the search for exoplanets or whatever, this is what I call a personal journey film set against the backdrop of scientific investigation. So it follows a single character or a group sort of cast with a supporting cast for a number of years. So we followed Larry and his people who were helping him for about 5 years. I do want to say that I am not a scientist. I did not have any sort of expertise in astronomy before I started this project. I can now carry on a pretty advanced conversation about one specific niche of astronomy, and I've really developed an enthusiasm for it as I've gone. But I am first and foremost a storyteller. So you're going to see not just the science, but also the human element in this film. When we finish during the Q&A, the first thing that I'm going to do is I'm going to show you a few plots, because I know that the astronomy folks I get comments like, I couldn't even see the axes on those plots. And so I'm going to sort of address some of the scientific questions that most often come up immediately at the end of the film. And then we'll open it up for a broader Q&A. And I also just want to quickly share my screen with you, so to make sure that we can all make the transition here to the screening platform. So you should see my web page here where I know that this is not your group. I'm just using it as an example of an event that I have not yet registered for. If you go to the link that was provided on the OCA webpage, you'll see, if you haven't registered yet, you might see this orange register button. And so you would need to click it and enter your information, email address, full name, and then make sure you check this box. This information is just coming to me. It's not going to this company. The only reason you're entering it is because I want to have a way to contact you once the film is available to let you know that it's available. Either, hey, you can purchase it now from the website, or hey, guess what? It's on Netflix, you know, as the case may be. If you've already registered for the film, you might see this. You don't see the register button, but you do see just a watch trailer, but you don't see the orange watch now button that we're hoping for. If that's the case, it's probably because you loaded the page before the event technically began, 11 p.m. my time, 8 p.m. your time. If that's the case, just reload this page. And now that we're after the time that the screening has started, that should transform into an orange watch now button. So what I want to ask everyone is, do you see this orange watch now button on your page? If you do, could you please use your hand icon to raise your hand, and that way we can know that everyone is with us. If you are having questions, you can put them in the chat, and we will see if we can respond to those. I'll mention some of the things that sometimes happen as you all are working on this. Occasionally people will say, oh, I have to register twice. I already did it, but I'm having to do it again. Maybe that's just a different browser you're using or something like that. So it takes about 20 seconds to register, and then you should be able to get this watch now button. So I see two people. with their hands raised. I saw another person raise it and then put it back down. If you could leave the hand raised, that would be helpful, so we can just make sure that we've got everybody with us. And I think in the interest of time, we'll probably wait until we've got more than 50% and then proceed. Thank you, Reza, for putting the link back in the chat. And I'll raise my hand. I'm following along just so I can have a preview. So we'll give it another minute or so. Perhaps some folks have stepped away at the beginning of the webinar. If you're having any technical issues, feel free to send a chat and I will respond. And that goes for even after we've started the screening. If you're having any technical issues, please just type your questions into the chat and I'll be watching that as we go. Reza, I'll defer to you. Do you think we should go ahead and move forward or give it another minute?
Yes, I think people who have already gotten into the Watch Now button, we could get started for those. And let's maybe re-say what's going on for the people who haven't yet, just in case they have any problems.
Okay.
So if anybody has any problems, please do put it in chat and we'll be able to help you.
Yes. So just to recap, go to the link that Reza just put into the chat. If it's prompting you to register, then you can click register and you can just simply enter your name and your email address and check that box. And then you should come up with the Watch Now button. And in just a second, we're going to say ready, set, go. We're all going to press the Watch Now button. You'll be in control of your own viewing. So if you need to stop and get a drink of water or whatever, you can do that. And then I'm going to put up a graphic. In fact, I'll go ahead and show you what that says. I'm going to stop sharing my screen. I'm going to put this up during the screening, and this just gives the link, and it says the Q&A will begin at 9:05. I'm guessing it's going to be a little bit more like 10 after. The film is 60 minutes, and then there's about 2 minutes of credits. So we'll let that roll and probably end up starting the Q&A around 9:10, 9:12. All right. So with that, if everyone could sort of on the count of 3, get ready to press that Watch Now button. And please remember to mute your mic. Stay in the Zoom meeting, but mute your mic. And we'll see you in about an hour. Okay? Thank you very much. All right, everyone with us? We reached the end of the film, hopefully. So let me share a couple of key graphics with you, and then we will open it up for questions. All right, this is the main plot that sort of begins. Am I sharing screen? No, I didn't. Share screen. There we go. Okay. This is the main plot that sort of gets everything going. This is called the O-C plot. It plots the observed eclipse against the calculated eclipse. So basically the idea here is that if this binary star had a steady period, had a constant period, when would these eclipses occur? But then how does that compare to when they are actually observed to occur? And what happens is that they seem to come earlier and earlier and earlier. So that is why over the course of time on the x-axis, the observations at first by Kepler in the green, well, actually first NSV and NSVS, and then another survey here, the WASP survey, and then a lot of rich data from the Kepler project. And then eventually the Kelvin data that they take for several years, it continues to go down and down and down and down and down. So this is just indicating that the eclipses are coming earlier and earlier and earlier. And this dotted line is the curve that was generated by the equation that Larry derived from V1309 SCO. And he said, given all the parameters of that star, what would our star have to do? How would it have to behave in order to be sort of on track for the same result? And so he gets this very specific parabola. This is not, as he says in the film, it's not an equation that you can just keep tweaking different knobs and make it say something different. It's a very specific formula, and this is the curve he gets. And indeed, the behavior of the star follows for about 4 or 5 years, almost exactly what the predicted behavior was. This is, let me go to full screen here. This is, you get a brief image of this when Kara is presenting the results of the spectroscopy. Oops. Essentially what this is this is the spectra of a broadened binary. So you have this binary star that has the bigger star, one of the stars moving towards you as the other one is moving away, and then vice versa. So any star is going to have a little bit of a red shift and a blue shift by virtue of one side of it moving towards you and one side moving away. But this is an even broader spectra because the whole system is moving towards you or away. And what they're looking for is the signature of a third body that is relatively stationary in the sense that the two are orbiting maybe at a 20-year orbit around the one. And so if they were to see the signature of a third star that's not moving very much, it wouldn't be very much shifted red or blue, then it would be sort of a single spike like that. And because they don't see that, that's when they conclude that there is not definitively a third body. Then we come to the typo. So this is one thing that people ask about a lot. And it just, for the general audience, it's a lot to explain here, but this is the concept of modified Julian date, which some of you may be familiar with. So if you want to study something that happened, millions and millions of years ago, how do you be consistent with talking about time? You have to use a sort of serialized system for referring to however many days ago it was. And they modified that number. They take off a lot of the insignificant digits to save space when they put it in a paper. But there are different conventions for how to modify the Julian date. And one of the conventions is to add this 0.5 at the end. Why do they do that? Because that way your observation day spans the whole night rather than the night being split between 2 different days. But other systems, other surveys, other projects don't use that convention. And it's just a matter of stating which convention you use. So to the lay audience, I sometimes describe this as if the people whose paper they were using said they were using inches, but they were actually using centimeters. It wasn't a calculation. It was a unit of measure that was misstated. And what's really interesting about it is that in the preprint archive version, that figure was correct. And that's the one that Quentin used, but in the official published version, it was wrong. So somehow in the process of getting actually published, the figure was changed. And we've never gotten to the bottom of that mystery because it was, over 20 years ago. This is the same O-C plot that we talked about at the beginning, but you can see here the new plots that San Diego State found. So they saw all this empty space, and they said, boy, it would really make this prediction stronger if we could fill in some dots back here. And they made a request to NASA to access the data from the Vulcan project, and they thought this point was going to come in down here on the curve, and when it didn't, they had serious questions. So they checked this data, and those numbers matched. But when they double checked that point, they got a point way up here. How did they do that? Because, as we mentioned, the modified Julian date was 0.5 days off. It was half a day off. And the period of this binary system is 11 hours. So a half day minus the 11 hours is a 1 hour difference. And that 1 hour difference was enough to not be obviously a mistake when Larry looked at the data. So he plotted it down here. And of course, the second derivative of this parabola is much more extreme, because that's what we're looking at, is how fast is the rate of is the acceleration speeding up, right? And if it starts up here, it's not nearly as extreme of a parabola. Let me back up and say one more thing about this. Since the project finished, they actually Harvard has 100 years worth of photographic plates of data that has been sitting in a basement for years and years and years. And they finally finished this massive digitization project, and just a couple of years too late. And what they found when they looked back at a century of data on this star, which was incomplete, but they had enough to see that it apparently goes through these swings where it goes maybe 30 years of increasing period and then going back up. But they know there's not a third body, so they really don't know what's going on with the star. It's still sort of a mystery. This is a histogram that plots period derivative against period. And this was the key to discovering the 7 new stars in the southern sky that are the subject of the new investigation that starts at the end of the film. So essentially what Larry did was he used data from the Ogle survey and that he had found in someone else's paper. And he plotted all these stars, and these two horizontal lines indicate that within this range on the y-axis, he believes that basically all these are probably all the changing of the period derivative, either positive or negative, is probably caused by a third body. And if we were to go back and look 10 years later, some of the ones that are towards the top would be towards the bottom, and vice versa. So there's a pretty equal distribution. But what really stood out to him is the total, the tail of this distribution, which as the period gets longer, there seems to be a few stars with very negative period derivatives, but none up here to match. So that was very telling to him. What's going on with the tail of this distribution? Why are these stars down here? And essentially what he's developed is an explanation of the evolution of binary stars in a few stages. And over the course of the time, millions or billions of years, as these stars evolve, they get to larger and larger periods and more extreme mass ratios. That's not on this plot, but more and more extreme mass ratios, until the point at which it reaches a critical mass ratio and it starts to lose angular momentum and begins to spiral in. And that's why you see all these stars decreasing their negative period derivative. And when we went to Chile, what he was looking for is the most recent light curves he'd had on these 7 stars were about 5 years old. So if he were able to check after 5 years and see that the period was still decreasing for all 7 of these and that none of them had turned back around, that would be strong support for his theory. And that's exactly what he saw. This is hot off the presses, and this was just recently, a few weeks ago, that he gave this to me, and this sort of summarizes. This is the most recent poster presentation that he's developed, and it sort of illustrates that he's continuing to work on his theory for how binary stars evolve, and he's making progress. He's discovered a new initial instability, that systems that form with a mass ratio of greater than 0.7 have this other instability that they encounter. So he's continuing to refine that theory, and then he's going to move on to basically the statistical work of saying, all right, if we know what the signature is of stars that are about to merge, because in this histogram, as Andre says in the film, these stars we think are within about 10,000 years of merger. Well, if you can scale that up and search bigger surveys, And if you can find 70 or 700 or 7,000 of these stars, eventually statistics say that you'll find one that's within, say, 10 years of merger. So that's sort of what's on the horizon. I will also put a link in the chat here. I'm going to stop sharing my screen, where I have all of the graphics that I just shared available for you to look at. So if anyone wants to take a closer look, especially at this last poster, because there's a lot of detail in there, then you are welcome to do that. So anyway, that's my brief spiel from a non-scientist trying to dive a little bit deeper into the scientific aspects of the film. But I would love to hear y'all's thoughts and respond to any questions that you might have.
Thank you, Sam. Just to echo one of the audience's verbs, amazing, motivating, exceptional, and an interesting documentary, which inspired us to be more extraordinary. Thank you very much. That was great.
Thank you.
And definitely, you know, the first thing I wanted to see after documentary were the graphs. Thank you very much for fulfilling that also.
Yeah.
And we also have John Hood, who has a live view of that same star for us. Is that right, John?
Yeah. This invitation took me into a deep dive into this. I actually worked short period binary stars, vetting the data at high cadence. So this was very close to home in terms of the topic. I'm going to enlarge this, and then I'm going to figure out how to screen share it. So I put my observatory on it tonight, and I'll sort of give you what didn't happen first, and then I'll show you the star.
Sure. While you're doing that, let me also mention that we have this program at Orange County Astronomers, Cosmic Adventures, which we are doing very similar work looking at eclipsing binaries. Oh, you have a clean graph. Perfect.
Yeah, so I went and took his numbers and his model, and I plotted it for impact, if you will. And the reason is, of course, I'm actually taking a close cadence on it tonight, and I'm sure it probably won't end up having an 8.3 hour period. It will probably be back up at its, whatever it is, 4.7 odd, 0.47 days, 11 hours, give or take. But, you know, if I was looking for supporting evidence, you know, maybe, you know, it'll crash. This, I'm not sure I'm sharing the right thing now. So let me talk about a new share here. And the new share here is what I want. And here is the real-time picture. I'm taking a sequence of 3-minute exposures of this for this evening. Few clouds got in my way early, but I will get about 6 or 7 hours worth of data. This is getting a little far west in the sky, but the star we're talking about is right here. It's a 12th magnitude star. Actually 12.21 is the catalog V magnitude for it. And so it's not a naked eye star. It's you know, 6 magnitudes below what you can see with a naked eye. You're going to need a telescope. This is a 3-minute exposure through a 10-inch telescope through photometric filters. So if you have a 6 to 8-inch telescope and a dark sight, you can go put your eye on this. Kepler was phenomenal. It stared at this region of Cygnus, which is where this is located, continuously for years, and produced, because it's above the Earth's atmosphere, there's no scintillation or anything, very, very precise photometry. And people to this day are still finding new things in the Kepler data. It was looking for transits of exosolar planets, but we had a speaker recently that told us that they were using that data to actually do stellar seismology, that it was so sensitive they could see the shock waves that move through stars and determine their densities and other properties about red giant or red dwarfs. I can't remember. I think it was on the red giants, but I have to go look at my notes. But the data is phenomenal. So And the thing about being even an amateur scientist is, if you go to the British Museum and you're an amateur paleontologist and you want the skull of Peking Man for the weekend, security takes you away in bracelets. If you're an astronomer, you get a telescope and you point it up. The data is all there, real time for you. So that's part of the joy of the hobby or of a career. You have every physics experiment you can imagine in the universe up there. It's your job to figure out which one is doing which experiment. So let me kill this share. How do I do that? There we go.
Stop share. Wonderful. Thank you very much, John. This was very pleasing to know. And actually, one other point, Dr. Welsh, who was mentioned from State University of San Diego, was our speaker a couple of years ago.
Is that right?
Yes. So that's another thing to note. That's great. So we had some questions during the presentation that you did already answer, but just for the benefit of everybody, can you go over that? There were questions about, well, you already answered. It's 12. John already mentioned that it was a 12th magnitude star, not visible with naked eye. And somebody asked about the distance and about the what is significant about red supernova. Can you answer that again so that everybody can hear it?
Right, sure. So the star is about 1,800 light years away. And at first they thought it was more like 1,000. And in fact, there's a scene. So what you just saw is a 60-minute cut of a 90-minute film. And one of the things that you didn't see was a really interesting scene where the group goes to Chaco Canyon, which is in New Mexico, sort of near where the remote observing site is. And they see a pictograph of a nova that exploded, I think in 1056 or 1058. I can't remember, in the Crab Nebula. And they talk about this, and they're walking around these ruins of this Chaco culture, this ancient civilization. And they're discussing the fact that if he's right about the prediction, then the light from the star has actually been traveling ever since that civilization was at its peak. So it's a really fascinating scene. Of course, they end up finding out later in the timeline that they were a little bit off on the numbers. It's more like 1,800 light years away. Why is it red? I can't give you the physical explanation, but I can say that these phenomena are not very well understood. I mean, we're talking about just a handful of objects over the last 30 or 40 years. And the big ones are V38 Mon. So V38 Mon was in a part of the sky that we can actually see pretty well. So it wasn't that we were watching it beforehand, but when the outburst happened, we said, oh my goodness, look at that. And we pointed the Hubble towards it, and we took some amazing images that I'm sure many of you have seen. That's the image when they're in Seattle at the conference, and he's pointing and said, this is what it might look like. And you can go online and you can see the light echo from V38 Mon, and it is a very distinctive red color. And then in 2008, V1309 SCO was a star that had an outburst in a much more crowded part of the sky. So we weren't able to actually get images of it. But we were lucky in that it was captured in a survey. I mean, that's not what we were looking for, but Ty Linda was able to go back and look at the light curves and find that sort of death spiral and see he was able to see that it was a binary star. We didn't even know that it was a binary star, and that it had sped up and gone through this death spiral. So you kind of put those two things together. The V38 Mon, we have the after picture of what it looks like. The V1309 SCO, we have the before, like what our best approximation of what happened before. But we've never gotten the complete picture to anticipate it before it happens, to understand it well enough to know what to look for, and then to actually see it happen. And that's really the holy grail for Larry, is to be able to take advantage of the opportunity to see it happen, so we can gather all that data and really understand it thoroughly.
Okay, and I'll add just a little bit about the redness.
Please do. Thank you.
The current hypothesis, and that is the key word, hypothesis, is that unlike stars that do core collapse because essentially they've run out of fuel, this is where essentially a large amount of mass is dumped on a middle-aged star before its time. And because of that, its convective region is large and full of heavier elements, and the thing detonates and blows that chromosphere, which is all but gone, in a mature star, out around it, creating this dust. And dust absorbs shorter wavelengths of light, but the red light gets through that dust. That's why we're building infrared telescopes. We want to find out about all that interstellar media out there.
Mm-hmm. Yeah, and if you look at the light echo of V38 Mon, you can see that dust cloud around it. Yeah, getting bigger and bigger.
And just a question came that I believe you just answered that, John. Somebody's asking, would contact binaries emit shells of gas? And yes, they do, right? That was what you said.
When you look at contact binaries, before they blow, what you actually see is hot spots. The matter being taken off of a donor star onto the receiving star spirals in and becomes compressed as it tries to merge with the other star, and it creates a hot spot, like someone's setting a blowtorch on the star. And so you actually see hot spots rather than cold spots or dark spots. They actually see more blue. And if you look at one of the ways you tell binary stars from pulsating stars is their light color changes differently. When they're side by side, as we look at them, okay, you get the sum of the two colors. Then this color dominates, then that color dominates. And it's exactly backwards from pulsating stars. When they get bright, they get bluer, all right? But you'll see a different pattern. But you'll also see these blue spots. And when you're modeling binary stars, there's a lot of work because they also have star spots. So they got dark spots, and then they got hot spots associated with an accretion disk, which isn't necessarily synchronous with the orbit of the stars. And it's a real fun mathematical problem to work on.
That's a nuance that doesn't make it into the film, but disentangling the star spots and the way those affect the light curve was a real challenge to even get to the point where you have a clean light curve that actually is telling you something about how it's behaving. Yeah. Actually,
one of the things that one of the papers subsequent to this new data point correction has worked on it, and one of the causes of the apparent oscillation of the period is, in fact, there appears to be in the atmosphere of, I believe, the larger star, a red star spot which orbits because of the tidal locking at a period just slightly different from the period that the stars rotate. And that beat frequency between the red spot showing up and the occulting of the smaller star causes the period to oscillate. That's one of the current theories of what's going on here. So my data points tonight probably will go help solve that problem.
Excellent. And we have another question of scientific explanation. So you mentioned that this discrepancy between using the Julian day and modified Julian day ended up with half an hour in the graph. But to us, looks like the difference is 50,000 days and 0.5. So yeah. Can you explain that again?
Well, I mean, that's true. But I think that, I mean, I believe that they were able to account for the 50,000. I think that the half day was really what got them off, because I remember asking Larry exactly that question. There's another 5 way over here, and he said, "Yeah, but that's not what threw us off." I mean, the way that we were calculating it took that into account, but it was the 0.5. And I guess you can think if you go back 50,000 days, the real telling thing was when he looked at where was the star. And he said, "Oh, for us, it would have been below the horizon." So we knew that we were we were 12 hours off. If you go back 50,000 days, it's still going to be, up in the night sky if you've got the half day right. But the half day is really what screws you up in terms of, being way out of sync.
Yeah, that data came from Texas or New Mexico. I can't remember which, but
I think New Mexico. Yeah.
Yeah, but what you're trying to do here is to match the decay of these periods, and so you have to account for 12 hours of change, all right, even over a period of 5,000 days. That's a big difference. So when you move that down a half day and all of a sudden the numbers all line up, but you've got something else going on. And actually what the the gold standard here is it also, remember, the Earth goes around the sun. And so when we're on one side of the sun, we're moving towards it. All right, and we get the light early, and then we're on the other side of the sun, we get the light later. Okay, and you get an annual variation in things. And because the Earth's orbit isn't perfectly circular, you just can't just add and subtract number. What we work with is actually called a barycentric Julian date, which is the mutual center of gravity between the sun and the Earth. And you have to correct the light time for the, it takes 8 minutes for the light from the sun to get to us. So potentially you've got a 16-minute variation in the arrival time of the light that you have to sort out. And of course, time is not continuous. We get leap seconds and we throw them away. So keeping track of the barycentric Julian date in archival data and measuring it to years is yet another adjustment that you make when you start working at this level.
Okay, excellent. And now let's diving a little bit about the filmmaking side of it,
Yes, please.
Sam. So this is the classic question of making such documentaries. So first, you were tipped off that there's such a thing happening that might be very interesting, and you started contacting them. So how does it work? Do you regularly phone them and ask them, is there anything going on? Should we come, or do they call you when they're expecting something? How's the arrangement?
It was a little bit of both. It eventually got to the point where, he would definitely let me know. And I guess when it was first pitched to me by Matt Walhout, who you see in the film, it was clear to me that the period of uncertainty about the outcome was highest at the beginning. At least so we thought. We thought that over the course of time, he was going to become either more and more sure that he was right, or more and more sure that he was wrong. And of course, if you wait until he knows the answer to that question, then it doesn't make a very interesting film, because the interesting stuff is the drama, the suspense, right? So I said, all right, this is very interesting. Let's do it right now. Let's go ahead and raise a little bit of money, and let's do some shoots. Let's plan some shoots. So we went out to New Mexico. We started filming at Calvin. We went out to New Mexico that spring, and we wrote a couple of grants, and it was kind of like, if he's right, we'll continue to follow this and it'll be a feature film. If he's wrong, we're going to make a short film about the relationship between the school where that remote observatory is and then Calvin. It's basically on Navajo land. It's an interesting story, a completely different story. Well, it turns out that, they look for and we went to Apache Point, we went to Wyoming that summer, all these places. And it turns out that, lo and behold, the unlikely, as he says, the unlikely explanation was correct. There was not a third body. So then, okay, all systems go, and we're following it. We go to all the conferences, and finally he announces it, all the press coverage. And then about a year and a half later, it was actually interesting because I had stopped filming quite as much. We were pretty sure that he was right. And so I was actually focusing on expanding the scope of the project, raising money, because if he had been right, there would have been amateur astronomers watching the star everywhere, and how do you capture this whole thing? Hopefully the Hubble would have looked at it or something like that. So I was in that mode and not shooting quite as often. And then one day I go into their office and they throw that paper down in front of me and they say, it's not happening, And it just, as much as it might feel like a punch in the gut for you, if you're watching this and you're not familiar with the outcome of the project, it was even more so for me. Right. But we filmed as much as we could in terms of him delivering the bad news to other people, Matt and Larry having the conversation about it. And then the Chile opportunity came up, and that seemed very clear to me that was important for our story. And we thought it was going to happen during the summer, but it ended up happening during the semester. He and I are both full-time faculty members, and he couldn't get the time to go away. And I said, well, I have to. And so I took a former student, and the two of us went down to Chile by ourselves and we're sort of embedded with that team of astronomers to cover that side of the story, because we felt like it was a really important piece to have for the ending. And of course, I think that the story is not at all a complete loss, in the sense that from a scientific standpoint, a good theory is actually more important than getting lucky. So I know that for the average viewer, it's very deflating that the one star isn't going to be a naked eye object in the sky. And it is for all of us. But the fact that he really has developed a theory, and he has seen this path forward is still a very good ending in my mind.
Great. And was Larry the only person in the AAS conference with a filming crew following him, or were there other astronomers having done that?
There weren't. I mean, obviously at the press conferences there's cameras, but I don't think there was anybody else there who had someone actively following him. It's interesting. The first AAS conference in 2015, when he discovers right before he goes that the third body is still a possibility, is it happened a week after my oldest son was born, so I couldn't go. So I had to have a friend go for me. And then the one where he announced the prediction, I had school commitments that I couldn't get away, so I had a student go down there for me. So the only one that I was there personally for was the very last one, where he's talking to Andre Pecha and doing the digital poster and stuff. But no, in my experience, there was not any other camera crews.
So no other filmmaker was making a documentary about any other astronomers?
Not that I saw, no.
Well, the AAS has a whole press room where news media sits and people get invited in to talk about their stuff. I'm certainly, he got a lot more time than most papers got that particular meeting, but
oh yes,
there's always some news that comes out of those meetings.
Oh yes, it was everywhere, and all the news outlets all over the place were emailing me to ask me for the video content that I'd already shot. I think our trailer for the film, our early trailer for the film, got like 60,000 views in just a few weeks right there. So it was certainly an exciting time.
And speaking of the ex-students, I know John has something to add to that. So what are they doing now, Daniel and the other students?
Well, last time I saw Daniel, it was at an SAS conference, which is about small telescope science. If you've heard of Alpaca, if you're an amateur astronomer who knows ASCOM, it's been evolved such that you can have distributed computers and telescopes working together using that interface standard. And Daniel is the lead developer for that technology, and I believe at least at one time, if not still, is working for a manufacturer of astronomical instrumentation in Michigan. Was the last I knew of it, but he may have moved on from there.
Yes, Optech. I think, as far as I know, he's still there. I haven't seen him in a while. We're going to do a virtual event in a couple of weeks for people who were in the film who haven't seen it yet to see it, but he was a computer science and physics and astronomy double major at Calvin, and he is putting both of those things to use. And I remember when he was a senior, they were having some sort of problem with the telescope, and they went to Optech to ask it for it to be fixed or something like that, and they didn't know how to do it, and he did it, and then they hired him. It was a pretty fun story for him. So, and then the other students are mostly at different graduate schools. One's at Iowa, one's at Wyoming, one's in Maryland, and then a couple of them I'm not quite sure about.
So the film spans 5 years, am I right? And that's like two generations of students, or a lot of students there at the ending, at least. Right.
Well, he got an NSF grant after, and so he was able to hire more students. He used to have only one every summer. So Dan, and then Kara, and then there's actually, because again, it's a shorter version of the film. If you're an astute observer, you might notice that we just jump forward 1.5 years in this version of the film. And during that 1.5 years, basically what happens is it's kind of about the struggles of working in academia in a small college, and he doesn't have the time that he needs to get the paper done. And he's having to do the grant writing, he's having to do the teaching, and there's prioritization happening at the college where budgets are being cut, and he's actually sort of potentially in danger of losing his job. And so he's got a couple more students in there. And then, yes, there's a group of 3 at the end who really take it to the finish line, but he's still got another student who's not in the film who's working on it right now. So.
Okay, great. And so is Calvin providing graduate studies in physics as well, or is it just an undergraduate major? Or?
Well, that's, no, it's not even a major. So this is one of the sad parts of the story. So it's a physics and astronomy department that has an astronomy minor. That's all that it has is an astronomy minor. And that's one of the things that I was attracted to at the beginning, was this sort of underdog story, that it's not the type of place that you expect for a cutting edge project like this to come out of. Unfortunately, I mentioned the prioritization that was happening, a lot of schools, budget cuts and whatnot, and COVID just made that worse. And the school actually cut the astronomy minor this past summer, despite protestations from me as well as from them, saying, hey, we're about to put this thing out into the world that's about these students, and this program. And so we have yet to screen it. We're going to be screening it at Calvin for the first time in October. And I'm very interested to see how that conversation proceeds. But no graduate students, no postdocs, all undergraduates. And for the duration of the filming, it was only an astronomy minor.
Okay.
Yeah, there are a lot of astronomers that I know, okay, who came to astronomy from small liberal arts colleges. All right. If you're going to be an astronomer, undergraduate is too early to specialize. What you want to do is a lot of mathematics and a lot of physics, and yes, a little astronomy
Right.
to whet your appetite. But you move from there to a graduate program somewhere. And again, you still take lots of math, lots of physics and astronomy, because the job market for astronomers is pretty tight, and you really need to have sort of a backup and a skill set in physics and mathematics sets you up to do a lot of things. It's good to see people like Larry, who are gifted astronomers, who choose to teach at small liberal arts colleges. I'm working with another person here at SOCA University, who's in a very similar situation, and I worked with him at Las Campanas in Chile, and he's doing great things. And that's where many of the people that you find professionally get their starts. What's always remembered is where you got your last degree, not where you got your first.
That's right. Yes. Larry's concerned that because they've cut the minor, that he's no longer being able to offer the courses that the students would need to go into graduate school in astronomy. So I don't know. And to keep the observatory running as well. I mean, they have this twin telescope setup, which is really unique for a school of Calvin's size. We're talking about an undergraduate institution that has 3,000 students. And so it remains to be seen whether he can continue to get research students. If he can't get research students, he won't be able to get NSF grants. Can he keep everything going? We'll see. That'll be, so he and I have talked about doing maybe a 1 or 2 minute update video each year and just putting it on the website, just to help people continue tracking the story to see whether or not, he actually does end up succeeding and what happens.
So Sam, can you tell us a little bit about your own story? You said you're a professor of filmmaking there, right?
Yes.
And
right.
What kind of projects were you working prior to that, or simultaneously as you're working on this? And how much of a change in type of work you do is this documentary?
Right. Well, so yes, I mean, speaking of small liberal arts schools, I went to one. I went to Wake Forest in North Carolina. I'm from Tennessee originally, did all my school in North Carolina. I got an MFA in documentary filmmaking, and then I followed the job, as many of us do who are academics, can't be choosy about location. So we moved up to Michigan, to Grand Rapids, and I've been here for 9 years. Documentary filmmaking is what I do. It's sort of like my scholarship. Basically, I'm a tenured professor, except it's creative work instead of scholarship. And I don't have a particular topic that I specialize in. So a few of the projects that I've done, I think I was mentioning right before we got on the call, I did a cultural history of station wagons in America called Wagon Masters. And that was picked up by PBS. That was a really fun project. It's just a little half-hour documentary, but it was a lot of fun. I did a short about a couple in North Carolina who built their first home out of shipping containers. I did one about a high school football coach. I've done one about a dairy farmer. So it's a very eclectic, sort of very eclectic interest. But I think that one of the unifying themes is that I really like characters who kind of defy some of our expectations. And Larry is one of those characters. He is not what you would think of in terms of like the ambitious scientist who's out there to gain a lot of notoriety. He's actually gentle, mild-mannered, very humble. He's not seeking the limelight at all. There are other, I mean, one of the things that gets cut from this version of the film is a significant amount of backstory. For him, he taught at the University of Iowa, and he experienced both tragedy and failure there. And so I was very attracted to that, the sort of underdog nature of this story, but also just the wonder, I mean, that was something that I hadn't gotten the chance, and that, I'm a visual artist. So the idea of the sky being sort of a part of the film was very exciting to me from the very beginning, to think about shooting those sorts of things. So how has it changed? I mean, I do typically more short films. So this is my first feature that I've directed. I've worked on other features, but it's the first feature I've directed. So basically it just means that it's dominated my life the last, especially 4 years. At the beginning, I was doing it along with some other projects, but it's kind of like, if you're an academic and you write articles and then you decide that you want to write a book, it's sort of the same kind of deal.
And what about your connection to astronomy? Did you have any previous exposure to what astronomers do, or was that all new to you?
It was all new to me. I mean, I am an intellectually curious person, and I am inherently interested in the sky and the cosmos, and in the sort of human search for truth, I think. But no, I didn't know, for example, that astronomers are essentially applied computer scientists, that the degree to which they work with data, I mean, I had this idea of like, you're looking in the thing, and no. So the whole idea of like, what's a light curve? Like, what does it mean that, so there was definitely a learning curve for me to really understand. But over the course of time, I became a pretty poor proxy for a general audience because I was so immersed in it, and I became interested in it. And so I would become interested in these little technical details, and then I'd show it to a friend and be like, that, nobody's going to care about that. And it's like, well, I've come to care about these things, so that was interesting.
And the scenes we see from the Milky Way and all those time lapses, did you do them all yourself? And did you have to learn how to do them, or did you have an idea beforehand?
No, we did those all ourselves. Did them when we were in Chile. The key with those kinds of things is give yourself enough opportunities to get it right, So we were there for 6 nights, and we had 2 cameras, and we would I had a former student with me, so we would trade off during the night so we could make sure to get 2, 3, 4 time lapses at different places, different focal lengths, different frame rates and things like that. So which controls how quickly the stars move across the sky. And then, if you can get 20 of them, you're going to get a handful that are really good. And that's sort of what we did. So yeah, it wasn't terribly technically complicated. It just involves a lot of experimentation and staying up late, but that's not something that astronomers are unused to. So.
Okay, and at the very end of the movie, we see this promise of that they found a real way to continue their research. And then you're telling me that they're actually, the situation of the astronomy department in the Calvin College isn't future-proof, let's say.
Yes.
And you're still in touch with them. How do you see yourself in this project in the future? Are you going to continue filming, maybe a second documentary added to this, or do you think you've done enough? What's the proper prospect of your job here?
Yeah, I think that I need to keep shooting occasionally just to keep tabs on it and put something out there into the world, just because people, I mean, the way that film distribution goes, it'll be 2 or 3 years probably. I mean, my goal is to do 100 community screenings in 2 years, and then additionally film festivals, and eventually, hopefully you'll see it on Netflix or Prime or something like that. But so people are going to be contacting me, hey, what's the latest? It's been 3 years, what's going on? And so I need to be ready with an answer to that question. Larry is determined, and he is discouraged by the institutional situation, which I should make clear, it's not his department. His department's very supportive. It's the university overall. But I think that he would do it by himself if he had to, that would be a lot harder, but he has this goal now. And so I don't know if he ever gets it, if he does find it within his life, and if it is the kind of high profile thing where it is something that we could see naked eye, or it's nearby or something like that, I think that maybe then I would gear up and do something longer form to follow it up. Yeah.
And in terms of future projects, are you looking into doing another scientific documentary, or you probably going to go in another direction?
That's a good question. I have become very interested in sort of science communication, that field of trying to translate, because a lot of this, I mean, someone said it in the chat, it's a description of how science works, and I find that that's something that our world really needs today, is a better understanding of how science works. And so that is very interesting to me. I don't have any specific ideas, but I'm open to that. At the moment, I'm toying with something completely different, which is which has to do with cryptocurrency mining and things like that. So that would be a shorter project, but that's where my head's at. But still, 90% of my brain is with this project. A lot of times you talk to people like me, filmmakers, and they're talking about a film 2 years after they made it, and they've moved so far past that project and they're way on to the next thing. But you're talking to me very early in the release part, so I'm still very much in the thick of this project.
Okay, great. I believe I've covered most of the questions that we could have. John, do you have any other questions or comments?
There is a question up there about the mechanism for the spiral process. Gravitational wave energy from normal dwarf stars is not a big drag energy that would cause a loss of momentum. It's energy, it's mass transfer. It's the material that's peeled off the donor star that steals its angular momentum and causes the stars to move closer together. So that's the process. And there are, depending on the rate of that mass transfer, and this is something that Larry's been working on actually, if the mass transfer is slow and gradual, they will eventually coalesce into what's called a common envelope, and their cores will merge relatively peacefully with some helio-sized, or not helio, stellar seismographic impact. But if the mass transfer is a runaway because of a disparity, a large disparity in the masses, then you can dump a lot very fast, and that's when the stars come together violently. And those are the events that he is trying to model, and the models are interesting, and I'm trying to get my head around them.
Yeah, I mean, if you look at that histogram, as the periods of those stars are getting bigger, they're getting more extreme because of that mass transfer. And he thinks that there's this critical ratio, threshold ratio, I think it's 0.14, that once it passes that mass ratio and the smaller star is smaller than that, then it begins this runaway, I think is sort of the idea. You can correct me if I'm wrong, John, but that's my understanding of the, yeah.
Mm-hmm.
So, John, are you receiving astronomy telegrams as we speak? Is that you, the dings?
Yeah, unfortunately, that's me that's beeping. I've got something else going on here that is going to demand my attention shortly.
Okay. And Sam, you are on next day right now. You've passed midnight, right?
I have, but
okay,
that's nothing for astronomers, right?
Right. So, are there any final comments or notes you would like to mention?
Just please make sure that your group knows that the link is available for 3 days. And if you enjoyed the film, please share it with people that you know. They've only got 3 days. They need to register, and then I'll be able to follow up later and say, hey, it's available. So please share. That's what I'm trying to do right now, is just get it out there.
Excellent. Thank you very much, Sam, and thank you very much, John. And also, I would like to thank all the audience here being with us. Again, as Sam mentioned, the documentary will be available for viewing and reviewing for the next 3 days. If you want to see that again, or if you want to have other people watch it, you feel free to share the link. And with this, I would like to thank everybody and hopefully see you soon in the next OCA event. Thank you. Bye-bye.